Imagine, you've just finished programming a complex titanium aerospace structural component on like $1 million 5-axis machining center.
Oh man, high stakes right out of the gate.
Right. I mean, you've optimized the roughing cycles, you've meticulously dialed in the swarf milling passes for all those complex contoured walls, and, well, the simulation on your screen is just flawless.
Like absolute perfection.
Exactly. The kinematics look beautiful. So you post the code, you send it down to the floor, and the operator hits cycle start. You're standing there expecting a masterpiece.
And let me guess, that's not what happened.
Not even close. Instead, there's this terrifying microsecond of silence, followed by a violent scream from the spindle, and then bam! The tool holder plunges straight through the workpiece.
Ouch.
Yeah.
Total catastrophic failure.
Total disaster. You're looking at a destroyed $50,000 spindle, scrapped aerospace-grade titanium, and an entire production schedule completely derailed in a fraction of a second. But here's the thing. The underlying logic of the tool path was mathematically perfect. So why did it crash?
It is the ultimate engineering nightmare. And the really terrifying reality in that scenario is that the CAM kernel, the software, it actually executed its instructions flawlessly.
Wait, flawlessly? It just destroyed the machine.
Right. But the kinematic solver did exactly what it was asked to do. The failure didn't happen in the calculation of the tool path itself. The failure was embedded in the foundational data that the algorithm was using to construct its spatial awareness.
Ah, I see.
Yeah, so the computer was navigating a perfectly accurate map, but it was given the completely wrong dimensions for the vehicle it was driving.
Which brings us to the core of today's deep dive. We're analyzing a stack of documentation around ISCAR's NEO-ITA platform and their approach to digital tool assemblies.
It's a fascinating read.
It really is.
Yeah.
And our mission today is to dissect that exact friction point, the gap between the theoretical perfection of CAM software and the very unforgiving physical physics of the machine envelope. We're looking at how integrating ISCAR's heavily structured proprietary digital tool data acts as, well, really the only reliable bridge across that gap. So okay, let's unpack this. If the software is so incredibly sophisticated, how is it still so vulnerable to a spatial mismatch?
Well, the vulnerability lies in the legacy workflow of how we actually define cutting tools in a digital environment. Like, think about the sheer computational power of a modern CAM system. It can calculate complex chip thinning algorithms, dynamic milling routines, all of it dynamically.
It's mind-blowing what it can calculate.
It is. But historically, that system is completely blind to the physical world until a human being manually constructs a tool library for it.
Right.
And that process, it usually involves an engineer parsing through hundreds of pages of like PDF catalogs or even paper catalogs, hunting down a specific end mill or insert.
Oh, wow, yeah.
And then manually transcribing dimensional values into the CAM software's tool manager.
So we're basically asking highly paid manufacturing engineers to act as like data entry clerks.
Essentially, yes. And the risk profile there is just massive. We aren't just talking about inputting a primary cutting diameter and calling it a day.
Right. There's way more to it.
Exactly. To build an accurate topological model of a cutting tool, you have to define the cutting length, the non-cutting flute length, the shank diameter, the neck transitions, the corner radii.
That's a lot of manual typing.
And if you're building a turning tool, it's even worse. You're looking at insert inscribed circles, nose radii, approach angles, clearance angles.
And I imagine it only takes one typographical error, like a slipped decimal point on a shank diameter or, a misread clearance angle, to completely corrupt the simulation's validity.
100%. Because the software doesn't know it's a typo. If an engineer accidentally inputs a flute length of, say, 50 millimeters instead of 15 millimeters, the collision detection engine assumes it has 35 extra millimeters of safe clearance.
Oh, no.
Yeah. So it will confidently plunge the non-cutting shank of that tool straight into the raw stock. The algorithms are processing this phantom geometry that doesn't actually exist on the shop floor.
It's like using a GPS that thinks you are driving a tiny motorcycle, but you're actually driving a massive semi-truck. The path is mathematically correct, but you're still going to get wedged under a bridge.
That's a highly accurate way to look at it. The calculation is only ever as robust as the geometry it's applied to. And this is the specific bottleneck ISCAR is targeting with a NEO-ITA.
Right, their digital tool advisor.
Exactly. They are moving away from that manual transcription and toward a deterministic digital advisor environment. The workflow shifts entirely. Well, instead of searching a catalog for a tool and then defining it for the software, The programmer inputs the machining realities, so like the material class, the specific feature topology, the operation constraints.
And the platform just cross-references those constraints against ISCAR's database to pull the optimal item.
Precisely.
But the critical distinction here for you listening is that it's not just generating a generic theoretical cutting profile. It's pulling a fully validated digital twin of a specific ISCAR physical product tied to an actual ordering number, a real SCO that you can buy.
And the data structure is what matters there. It's feeding structured parametric data directly into the CAM environment.
Right, so it's a perfect match.
Yeah, it utilizes standardized data protocols, pulling in the exact 3D models and all the associated metadata. So the digital tool definition the software is using to calculate its boundaries is a one-to-one mathematical replica of the physical carbide that will eventually sit in the spindle.
So, okay, we've solved the geometry of the cutting edge itself. We know the end mill is exactly the size the software thinks it is, but the cutting edge doesn't just hover in the machining envelope by magic. It has to be held.
And that introduces the concept of system-level architecture in cutting tools. This is a core philosophy from the text we're looking at today. A cutting tool is almost never an isolated component. It's a kinematic chain.
A kinematic chain, yeah.
Yeah, you have a carbide insert, right?
Yeah.
Which has to seat perfectly into a specific pocket on a cutter body.
Okay.
Then that cutter body might thread onto a modular extension, which then clamps into a shrink-fit collet, which sits in a heavy tool holder, which interfaces with a specific spindle taper.
It's a whole assembly.
Exactly. Builds that complete multi-stage assembly digitally. It generates the entire hardware stack.
Okay, but let me push back on this for a second. If the holder hitting the workpiece is the problem, why not just always pick a super long, skinny tool to guarantee you reach the feature without the holder getting anywhere close? Why bother modeling all that complex holder geometry?
That is a very logical question, and it brings us right into the physics of machining.
Okay.
Because if you just use a super long tool for everything, you introduce massive uncontrolled overhang. And excessive overhang reduces dynamic stiffness.
Ah, I see.
Yeah, a tool that is too long will deflect. It will vibrate, which we call chatter in the industry. It will leave a terrible surface finish, and it will break prematurely.
So you can't just slap a 6-inch end mill on every job just to be safe.
Exactly. What's fascinating here is how NEO-ITA's assembly options allow the programmer to find the Goldilocks zone.
The Goldilocks zone.
Yeah, the exact modular connection that provides the necessary reach without unnecessary length, ensuring maximum rigidity. And it validates this virtually before you ever cut a chip, saving real-world money.
Right, because if you only model the cutter, the simulation is fundamentally flawed.
Completely. Modern CAM systems rely on dynamic collision checking between the tool assembly, the workpiece, and the machine kinematics. If your model ends at the shank of the end mill, the software will look at a complex 5-axis swarf toolpath, see that the cutting edge clears the fixturing, and validate the code.
But it has no idea what the holder's doing.
None. It has no idea that the massive steel flange of the tool holder is swinging on a B-axis pivot and is about to shear the trunnion table clean off.
Wow. So having the exact proprietary holder geometry imported seamlessly isn't just like a nice visualization feature.
Yeah.
It's a strict requirement for avoiding the crash we talked about in the intro.
Exactly. And establishing the exact gauge length, the distance from the spindle face to the tip of the tool, means the software knows exactly what the structural limits of that specific assembly are.
Okay, so we've successfully modeled a perfectly rigid tool assembly, and we've validated the spatial awareness to ensure we don't physically crash the machine. But spatial awareness is really only half the physics. I mean, a perfectly rigid tool will still shatter instantly if we drive it into a block of hardened steel using feed rates meant for aluminum.
Oh, without a doubt.
So how does a platform like NEO-ITA translate the physical geometry we just built into kinetic parameters like feed, speeds, depth of cut?
Well, the transition from spatial data to kinetic data is where the legacy manual process truly breaks down. Generating speeds and feeds is an exercise in thermodynamics and material science.
A massive amount of data.
It is. Historically, programmers rely on legacy shop knowledge. They look at an old chart, pull a base surface footage, and then dial it back by, 20% just to be safe.
Which introduces massive inefficiencies. I mean, if you run a high-performance tool too conservatively, you aren't actually protecting it.
No, not at all.
You're just increasing the cycle time and rubbing the cutting edge instead of shearing the metal, which introduces work hardening.
Exactly. And the physics of cutting different materials are radically opposed. Let's look at the thermal dynamics of machining titanium versus machining aluminum, which the source material digs into.
Right.
When you cut aluminum, it's relatively gummy. The material shears easily, and the vast majority of the heat generated by that friction is evacuated through the chip itself.
So the tool stays relatively cool.
Yes, but titanium is a completely different thermodynamic environment. Titanium is highly abrasive, and it has incredibly poor thermal conductivity.
So the heat doesn't go into the chip.
Right. When the insert shears the titanium, the heat gets trapped right at the cutting zone and absorbs directly into the carbide tool. If you use kinetic parameters designed for aluminum on a titanium part, the thermal shock will fracture the insert in seconds.
Here's where it gets really interesting.
Yeah.
NEO-ITA isn't just looking up a generic speed and feed chart. It dynamically calculates the kinetic parameters based on the specific ISCAR tool assembly you just built and the specific material classification you selected.
That is the crucial mechanism. The software knows the specific carbide grade of the insert, it knows the coating, it knows the exact edge prep and the rake angle.
Because it's ISCAR's own proprietary data.
Exactly. Because ISCAR engineered the physical tool, their algorithm knows exactly how that specific edge geometry behaves under thermal and mechanical load in a specific alloy.
That's incredible.
It calculates the optimal chip thickness, the entry strategies, the ramping angles, and the surface speeds required to keep the tool in its ideal operating window.
So it's essentially a closed-loop system of proprietary data. You aren't guessing how a generic tool will handle a cut. You are applying engineered data directly to the toolpath generation.
It replaces anecdotal guesswork with deterministic engineering data. And when you eliminate that guesswork, you achieve true process stability. You can confidently run the machine lights out, knowing the kinetic parameters are perfectly matched.
Wow. Okay, let's pivot from the thermodynamics of the cutting edge and look at the macro environment. We've established how this digital thread secures the simulation and the machining physics.
Yeah.
But how does this level of data standardization actually impact the physical ecosystem of the shop floor? Because, I mean, this isn't just a software exercise. There's an entire human logistics chain supporting that spindle.
Oh, absolutely. If you look at a manufacturing facility without a centralized digital tool advisor, you typically find a deeply fragmented logistics chain.
Like total chaos.
Pretty much. Engineering operates in a silo. A programmer might build a tool library based on tools they personally prefer, manually entering their own custom feeds and speeds.
Right.
Then a different programmer on the next shift does the exact same thing, but with completely different tooling choices and parameters.
Which creates a compounding data management problem downstream.
It creates absolute chaos in the physical tool crib. When tool definitions aren't standardized, purchasing ends up ordering redundant inventory.
I can imagine.
You have 10 different styles of half-inch end mills from 3 different manufacturers, all sitting in drawers, because there is no universal digital standard dictating which tool is supposed to be used for which operation.
And what about the setup operators?
They're left deciphering vague setup sheets that just say, like, face mill, forcing them to guess which specific holder and insert combination the programmer actually intended.
Yeah, that sounds like a nightmare. And the mechanism driving the NEO-ITA solution here is that rigid skew integration. By forcing the CAM environment to use specific catalog-linked digital assemblies, it creates an unbreakable digital thread from the programmer's desk straight to the purchasing department.
The ambiguity is completely removed. A tool in the software is no longer a generic description. It is a definitive bill of materials.
Right.
The setup sheet generated from the CAM software now dictates the exact ISCAR cutter body, the exact insert grade, the specific modular adapter, and the required gauge length.
So the setup operator doesn't have to interpret the programmer's intent because the intent is hard-coded into the setup documentation via the digital twin.
Exactly. And that standardization cascades into product lifecycle management, or PLM systems. Purchasing knows exactly what consumables are required for a specific job, inventory can be managed predictably, and the entire manufacturing process becomes a repeatable, documented system.
It's no longer just a series of isolated manual decisions.
Precisely.
You know, that brings up a fascinating point from the source material regarding knowledge transfer. When we talk about those isolated manual decisions, we're often talking about the intuition of veteran machinists.
Oh, the tribal knowledge.
Yes. You have operators who have spent 3 decades listening to spindles. They can adjust a feed rate override just by hearing the harmonic pitch of the cut.
It's almost like magic.
It is. They know intuitively which insert grade handles interrupted cuts in cast iron best.
But that tribal knowledge is highly localized and incredibly fragile. When that master machinist retires, their undocumented understanding of machine dynamics and material behavior leaves the building with them.
Which is a massive problem.
It represents a massive vulnerability for the manufacturing sector, especially right now with workforce shortages.
And NEO-ITA essentially acts as a digitizer for that intuition. By encoding ISCAR's decades of tooling research and applied application engineering into a deterministic algorithm, it democratizes that high-level expertise.
It creates a structured learning environment. A junior manufacturing engineer doesn't have to rely on trial and error or, hope that a veteran mentor is available to guide their tool selection.
Right, the software just shows them.
Exactly. The platform guides them through the workflow, demonstrating exactly which tool assemblies and kinetic parameters yield the most stable results for complex operations. The software captures the applied physics and makes it instantly accessible across the entire engineering department.
That's incredibly powerful. So what does this all mean for you? If we synthesize everything we've unpacked today, it really comes down to the absolute necessity of data integrity in high-stakes environments. You simply cannot build a reliable, automated physical process on top of fragmented, approximated digital data.
The output of the machine will only ever be as accurate as the input defining its environment. By integrating validated system-level tool assemblies and engineered cutting data directly into the CAM software, ISCAR is closing the loop between the digital intent and the physical execution.
It removes the manual data traps.
Yeah, the traps that cause collisions. It optimizes the thermodynamics of the cut, and it stabilizes the logistics of the shop floor.
The margin for error in advanced manufacturing has simply become too small to rely on manual transcription and legacy assumptions. The digital twin must be an absolute, uncompromised reflection of the physical reality, right down to the exact millimeter of the tool holder.
I completely agree. And if we connect this to the bigger picture, this raises an important question to consider. We are watching platforms like NEO-ITA successfully encode the highly nuanced, hard-won intuition of application engineers into reproducible algorithms.
Oh.
If the software can instantly generate the optimal tooling assembly and kinetic parameters for any material based purely on data structures, what does the future hold for human intuition in manufacturing?
Oh, that's a wild thought.
Right. In the next decade, will the next generation of engineers learn the physics of machining by observing the metal being cut, or will they learn it entirely from the algorithms that have already mapped the physics for them?
That is a brilliant friction point to leave off on. As the algorithms absorb the tribal knowledge, the nature of expertise itself begins to shift. Thank you for joining us on this deep dive. Keep questioning the data structures behind your processes. And remember, the next time you're watching a flawless simulation of a 5-axis toolpath, ask yourself if the computer actually knows the structural limits of the assembly it's swinging around. Because if it's just guessing on the gauge length, you're just one decimal point away from disaster. We'll catch you on the next deep dive.